Welcome to section 3.4 on partial fractions. So in a college algebra, you may or may not have looked at partial fraction decomposition. It's something that was always taught in college algebra class, but I've discovered that many instructors do not teach partial fraction decomposition. So this is something that you may or may not have actually seen. So I will be going over it. So what is this partial fraction stuff? Well, it has to do with a rational function. Rational function in the form of P of Q over Q, P of X over Q of X. So what does that mean? Well, P of X is a polynomial function. Q of X is a polynomial function. So the first example, that's a good example of what we're talking about. The numerator is x squared plus 3x plus 5. That's a polynomial function. The denominator is also a polynomial function, x plus 1. So when you have one polynomial function divided by another polynomial function, that is a rational function. And we quite often have to use partial fraction decomposition to rewrite the rational function so that it's in a form where we can then use some type of an integration technique. Because right now, there's no integration technique that we can use that's going to work on this. So the procedure here is really not too complicated. Step one is to make sure that the degree of the polynomial, P of X, is less than the degree of the denominator, Q of X. So if we look at example 1, the degree of the numerator, it's a second degree polynomial. It's a quadratic. The degree of the denominator is a first degree linear function. So the degree of the numerator is greater than the degree of the denominator. That's a no-no. The degree of the numerator has to be less than. We could do it equal to, but usually we like it to be less than the degree of the denominator. So how do you solve this problem? Well, you have to use long division of polynomials. Something else that you're going to have to go back to your college algebra and recall, doing polynomial long division. All right, so let's get into the first example here. So I would like to start off with red. Whoops. So this is a very simple example. We notice that we have a rational function, x squared plus 3x plus 5 divided by x plus 1. And the degree of the numerator is greater than the degree of the denominator. So we have to do polynomial long division. So the denominator is the divisor. That goes out here. The numerator is the dividend, which goes underneath the radical sign. And so there's lots of videos out there that will kind of explain how to do polynomial long division. If you need a more in-depth analysis of how to do that, please go to Organic Chemistry Tutor, Patrick JMT, Khan Academy, whatever you like. Math is power for you. There's lots of good sites out there. Or just type in YouTube polynomial long division. You'll get lots of videos. But we divide the x plus 1. We take the first term here, x, and I say, okay, x times what would give me x squared? Well, that would be x. X times x is x squared, so I put the x up here. Then step 2 is to multiply. I multiply x times x and get x squared, x times the 1 and get x. That's step 2. This is the same as normal division. Then we subtract. We put a subtraction sign here. X squared minus x squared is always going to be 0 if you did that correctly. And then 3x minus x is 2x. Bring down the remainder 5. Okay, so we bring down the 5. And we keep going with the division as long as the degree of this term is equal to or greater than the degree of the first term in the divisor. Well, this term right here is a first degree term. It's x to the first power. And the 2x right there is a first degree, so we keep going. So let me erase all of this. Let's do it again. So now what we want to do is we say, okay, so this is where we're at right here. Now we say, okay, x times what will give me this 2x? Well, x times 2 will give me 2x. So 2 times x is 2x. 2 times 1 is 2. Do you get that? And now subtract. 2x minus 2x is 0. 5 minus 2 is 3. So 3 is a 0-degree polynomial. And so it is less than this first-degree polynomial. And so we are done. Again, this isn't a lesson in doing polynomial long division. If you need to, lots of videos out there on how to do this. So the important thing here is that we now have, this is what we call the quotient. Okay, so the quotient goes here, and then the remainder. The remainder is 3, which we always put over the divisor. So 3 over the x plus 1. And that is what we're shooting for, because we can integrate each of those terms now. So breaking this up into its own radicals, we have the integral of x dx plus 2 times the integral of just 1 dx plus 3 times the integral of 1 over x plus 1 dx. And so we can integrate each one of those with known integration rules, and we get our final answer. So this is basically to kind of show you, to demonstrate the polynomial long division. Whenever the degree of the numerator is greater than or equal to the degree of the denominator. Number 2. So now let's get into the nitty-gritty a little bit more. Whenever we have something in the denominator that can be factored, we're going to factor it. So first of all, this basic rule right here tells us what to do with our polynomial. So I'm just going to explain it in the terms of doing this first example. All right. So in exercise 2, I notice that the degree of the numerator is less than the degree of the denominator. So I do not need to do polynomial long division. So the next thing that we do is look at the denominator. We need to factor the denominator. If you cannot factor the denominator, then nothing that we're going to do in this lesson is going to work, and you're going to have to try to come up with something else. So the denominator must be factorable. Well, this is not a lesson on factoring. So if you need to, find some videos on factoring polynomials. So I just went and factored this into these 3 factors. And they are all linear factors. That's why this section is on non-repeating linear factors. Okay, they're non-repeating linear factors. In other words, all the factors are different. There aren't 2 or more of any particular factor. You know if you have 2 or more factors because they're raised to a power, such as the x might be x squared. That would be x times x. Or x minus 2 might be x minus 2 to the 3rd power. That would be 3 x minus 2 factors. So each one is just raised to the 1st power. So here's what we do. For each factor, we're going to create a fraction. And so we have 3 factors. We have the factor x. Okay. We have the factor x minus 2. And we have the factor x plus 1. We put them each in their own fraction denominator. What do we put in the numerator? We put a constant. So the constants a, b, and c are what we're going to put in the numerators. The rule, if you read up here, is basically going to tell you that the term that goes in the numerator is always 1 degree less than the term in the denominator. Well, all of these linear factors, a linear by definition is 1st degree. So all of the denominators are first degree, so all of the numerators must be 0 degree, which is a constant. Constants are considered a 0 degree polynomial. And the reason for that, in case you're wondering, is so if you have 2 times x to the 0 power, well, what is that really equal to? Well, that's really equal to 2 times 1, because anything to the 0 power is 1, which is just 2. So if you have just the number 2, it can be thought of as 2 times x to the 0 power. So it's a 0 degree polynomial. Okay, well, that's just an aside. Okay. So now that we've got all of this, what do? We take our fraction, we take this, and we multiply both sides by the least common denominator. Well, again, this is not a lesson in how to simplify rational functions. There's a lot of college algebra in this particular lesson. To simplify a rational equation, rather, not a function, but a rational equation, you multiply both sides by the least common denominator. Well, the least common denominator is this denominator. It is that denominator. So I'm multiplying both sides of this by that denominator. So here's what that might look like. All right. So I'm going to take this over here and multiply it by x minus 2 times x plus 1. Now, again, I didn't show any of this because this is just basic algebra. And I took this side over here and multiply it by x minus 2, x plus 1. Okay, I'm just doing a real quick little review. But again, find a video on simplifying rational functions. So when you multiply the left-hand side by this all completely cancels out with the denominator, leaving you with just the numerator, which is, boom, what I have here. Then over on the right-hand side of the equal sign, in this first fraction here, the x's cancel out, leaving me with x minus 2 times x plus 1 times the a, which is what I have here. In the second fraction, the x minus 2 cancels out with the x minus 2. I'm left with the b times x plus 1. And then in the third one, the x plus 1 cancels out. I'm left with the c, x minus 2. Okay, so I did not show all of that work. I just showed the final result of multiplying both sides by the least common denominator. Once you get past that point, now you need to do all of your multiplication to simplify it. So multiplying these 3 terms together gives me this. Multiplying bx times x plus 1 gives me that. Multiplying cx times x minus 2 gives me all of that. Now, there's 2 different techniques that are commonly used at this point in time. One of them is called the equating of coefficients. Okay, and your textbook describes both of these. It may not call them the exact same thing, but the first technique is to equate the coefficients. And so that's what I'm doing at this point in time. That's what is going on right here. So what I do is I look on the left-hand side. What is the x squared? What is the coefficient of the x squared term? Well, there is no x squared term. It's 0x squared. Okay, so I just put a 0 here. And the reason I have to look for the x squared term is I have x squared terms over here. I have an ax squared, a bx squared, a cx squared. And so I put those on the right-hand side of the equal sign. So what I'm doing is I am equating the x squared terms. Okay, I have 0x squared equals ax squared plus bx squared plus cx squared. I go to the next term, which, I'm going to do each of these in a different color, is 3x. So I take 3x, set it equal to all of the linear terms, because 3x is linear. So I have a negative ax, a bx, and a minus 2cx. So I put those on the right-hand side of the equal sign, and I am equating the left and right-hand side linear terms. And then finally, I am equating the constants to negative 2a, and that's it. 2 equals negative 2a, which works out real nice because that's going to make this easy to solve. Okay, from there, we move over here. These are little arrows. So what we do to go from here to here is I get rid of the variables. All I do is I look at the coefficients. So I have 0 is equal to a plus b plus c. Same thing here. I get rid of the x's. I have 3 is equal to negative a plus b minus 2c. So if you've had some linear algebra in your college algebra class, this will make perfect sense. If you've never had any linear algebra, matrices type stuff, this is not going to make much sense either. And then finally, 2 equals negative 2a is just the same. So what we have over here now is a system of linear equations. We have a system of 3 linear equations in 3 variables. The variables are a, b, and c. Now, we don't really need to use any linear algebra to solve this. We can use what's called back substitution. Back substitution means I start with this right here. I know that 2 equals negative 2a, so therefore a has to be equal to negative 1. What I do from there is I substitute that into one of the other equations. So what I did was I substituted that into the second equation here, which gives me this down here. Negative a is negative 1, so a negative a is a 1, plus the b minus 2c equals 3. And that can simplify down into b minus 2c equals 2. And then I did the same thing up here. I took the first equation up here, 0 equals a plus b plus c, plugged in the negative 1 for the a, and that gave me this equation here. All right, so I've got 3 new equations, or 2 new equations, these 2 equations. So, okay, getting messy here. So I've got these 2 equations in 2 variables. So what I did was I reduced it from 3 equations and 3 variables to 2 equations and 2 variables. Now I'm going to use a process that you learned in college algebra called elimination to get rid of the b's. I'm simply going to subtract equation 2 from equation 1. So if you need to, find yourself a video on solving systems of equations by elimination. And so when I use elimination, I end up with c equals negative 1/3. Substituting that into either one of these equations, I get b is equal to 4/3. So 90% of this problem is just a whole bunch of algebra. Once we have all of these, what do we have now? Yeah, that's a good question. What do we have? We have a value of a, we have a value of c, and a value of b. So we go back to our original equation here, right? This meaning we go back to this, and we substitute in the a, b, and the c. Substituting in the a, b, and the c, we end up with this. All right? So all of that work, all of that algebra was just to get the a, b, and c coefficients. From here, it's pretty easy. All right? So we're integrating this, remember? So we're integrating each one of these terms. Well, they're all log functions, all right? They're all going to be log functions. So we have the negative log of the absolute value of x, 4/3 the log of absolute value of x minus 2, negative 1/3 the log of x plus 1 plus c. All right, so you got a lot of algebra to remember. And so polynomial long division might be one of them. Simplifying or solving rational equations might be another one of them. Solving a system of equations by elimination might be another one that you might have to do. There was a lot of stuff in here. Let's do one more, and then that'll be it for this particular video. Even though I got, we'll do this one. Okay, where should we start here? Well, I notice that the degree of the numerator is equal to the degree of the denominator. The highest powered term in the numerator is an x squared. The highest powered term in the denominator is x squared. So I have to do long division. Okay. So doing the long division, I'm not going to go through and explain that again. I did the long division here. See if you can make sense out of it. And so the quotient is 1. And the remainder is 3x plus 5 divided by x squared minus 4. So that goes here. Now, we want to try to integrate this. Now we're getting into the calculus part. And so, we can't. And so, the one we can kind of ignore for now. Our rational function is really just this part. We can't forget about the integral of 1. We can't forget about this part. But this is the part we've got to work with. Okay, so the techniques that we're learning now is just for the second integral. So x squared minus 4 is factorable. It can factor into x minus 2, x plus 2. So we break it up like this. Factor the x squared minus 4 into x plus 2, x minus 2. Then on the right-hand side, we put each factor in its own fraction with an a in the numerator and a b in the numerator because these are non-repeating linear factors. Okay, multiplying both sides of this equation by the least common denominator. Multiplying both sides by x minus 2 times x plus 2, both sides, doing it over here too. Well, they cancel out on the right-hand side, and you're just left with the numerator. And then so in the first fraction, the x minus 2's cancel out, and you're left with a times x plus 2. When multiplying the second fraction by the least common denominator, the x plus 2's cancel out. You're left with b times x minus 2. Now, I'm using the second technique that your book describes. I don't know what they call it, but they call it the method of strategic substitution. That's an interesting name, and it's an accurate name, strategic substitution. Let's see, why do we call it that? Well, what we want to do here is we want to solve this for a and b as simply as possible. Really, well, all we're trying to do at this point in time is find a and find b. So I noticed that if I was to let x be equal to negative 2, let x be equal to negative 2, like I write here, that this term here all just goes to 0. Because negative 2 plus 2 is 0. 0 times a is 0. And now over here, we end up with a negative 4b. And then putting it in over here, I get negative 2 times 3 is negative 6 plus 5 is negative 1. So I end up with negative 1 equals negative 4b, or b equals 1/4. So very simply, by strategically substituting a value in for x, I solved it for b. Then we do the same thing to solve for a. Okay, to solve for a, I say, well, let's let x be equal to positive 2. So when we let x be equal to positive 2, in this term here, we end up with a 0. And then in this term here, we end up with 4 times a. And then over here, we end up with 11. So we get 11 equals 4a, or a is equal to 11/4. This is a little bit easier in this case. Which one of these two methods, the one where we're solving a system of equations or this method of strategic substitution, depends on the problem. You have two different tools in your tool belt of mathematical techniques. You choose whichever one works. Okay, so we know what a is, we know what b is. So we can get to the calculus-y part, which means we are going to take our original, let's go back to the original problem here, get rid of some of the mess. All right, so our original, this right here, We substitute in the a and the b in the numerator. And so here's the substituting in the a in the numerator. Here's substituting in the b in the numerator. And of course, here was the integral of 1 dx. Remember I said don't forget that? That comes from right up here. Said don't forget that dx. That's got to come on down too. All right. So it looks like the antiderivative of dx we know is x. This again are both log rules. So the numerator, 11/4 times the log of the absolute value of the denominator, 1/4 times the log of the absolute value of the denominator. So the integrating is the easy part in these problems. It's the algebra that is time consuming. All right, that's it.